Hi, I'm going to explain IEEE paper of deadline constraint workflow scheduling algorithm for the infrastructure as a service clouds. In this paper, calling the assign parent and calling the assignment algorithm, we will learn how to assign the task to each resources and make the adjustment with the deadline at the same time. So for this, I will start with a very basic question that what is big data? Big data is the data we use every day through social media, public transport, and GPS. To store this data and to process this data, we do not need lots of big computers. Rather than we can use cloud computing to analyze a large number of data in minutes. This is the definition of big data. So now what is cloud computing? To explain you that what is cloud computing, I will take an example. Suppose a company has a big ideas to steam their business and to drive their sales to roof. To get this, they need business applications, but business applications are too expensive. And also they need the team of experts to stock all these applications. To make it cost effective, the company will use cloud computing instead of running the applications themselves. They will use shared data standards for this. They, they just need to plug in the utilities and it's faster and will cost less. Therefore, to run business companies do not need servers and storages, technical team to handle the applications, no software upgradation are needed, and all is done through cloud computing. Also, cloud computing is more scalable, more secure, more reliable. Now the question comes, why do we actually need cloud computing? It provides us on-demand resource provision. So whichever resources we need, we uh, just demand for that resource, and they are provided by their services is provided by to us by the cloud computing server, and it provides a homogeneous network. This means that it is comprised of computers using the similar configurations and similar protocols, and it also provides pay as you go pricing models. So we will pay only for the resources that we use and we need. We will not pay anything extra for the resource which we don't need and we don't use them. So now what is workflow scheduling in cloud computing? This is a very important thing in cloud computing. So as I said, cloud computing is a large network where resources are distributed over the network and are shared among its users. A service used by any user can produce a large amount of data, and he has to pay for the amount of data he used. So in this case, the data transfer cost between two dependent resources will be high. Also, a complex application can have large number of tasks, which may cause an increase in total cost of execution of the application if not scheduled in an optimized way. So, cloud computing aimed at the complete execution of the workflow by considering the quality of services requirements such as deadline constraint and budget constraint. So now, what is deadline constraint? Deadline constraint is a target date that indicates when the task has to be completed. Now comes the workflow scheduling algorithms that which we will do today. This one, first one is PCP. This is uh, this is grid computing algorithm. This is ICPCP, which is cloud computing algorithm, and this is ICPCP D2. This is also a cloud computing algorithm. So PCP stands for partial critical path. ICPCP stands for IaaS Cloud Partial Critical Path. ICPCP-D2 stands for IaaS Cloud Partial Critical Path Deadline Distribution. Now, what is the difference between grid computing and cloud computing? Grid computing is composed of many loosely coupled networks acting together to perform the same task. So these are the These uses a computer which are loosely coupled to each other, and they perform the same task. And these also involve a large number of chunkings which work in parallel. In cloud computing, instead of taking hard drive for the storage and CPU for the computation, it takes some services to provide them these resources. Now what is IaaS? IaaS stands for Infrastructure as a Service Cloud. It is an instant infrastructure provided and managed over the internet. It quickly scales up and scales down with the demand as we pay only for the resources we use. Therefore, IaaS helps to avoid the expenses and complexity of buying, managing your own physical servers and other data centers infrastructure. Each resource is offered as a separate service component, and you only need to rent a particular one for as long as you need it. IaaS provides us with the three things as you see here: servers and storage, networking, and data center physical building. And now we are coming on to the main topic for today, which is what is PCP. PCP is used to minimize the cost of the workflow while moving the deadline defined by the user. Now what is ICPCP and ICPCP-D2? These two algorithms are used to handle large workflows because they both have polynomial time complexity. Now there are two phases for PCP algorithm. First one is deadline distribution. So deadline distribution stands for that we have to complete the work or a given task in the particular given time. And also it depends upon the planning. This means the budget constraint. We have to schedule the task or in that way that we have to spend the less amount as we can. So execution of the task should be in the by providing the cheapest services. Before starting, I will like to tell you some abbreviations we are using in this paper. First one is T-entry. This is a node without any parent. T-exit, it is a node without any child node. EST is the earliest start time, as early the task can be started. EFT is the earliest finish time, as early the task can be finished. LFT is the latest finish time, as late the task can be finished. MAT is the minimum execution time, minimum time taken for the execution of the task. AST is the actual start time, actually at what time the task is being started. TT is the transfer time. So in this paper, in the first algorithm, we are using three equations. First one is EST. So EST is in the beginning. The weight of all nodes will be calculated as 0 using the fastest machine, so it is taken 0, the T entry. EST TI. EST this is EST of parent plus minimum execution time for parent and plus data transfer time from parent to the child. Right? And this TT is taken to be the constant. TT EPI depends upon the assignment. TT will be 0 if parent and child are assigned to the same machine. MAT is used to calculate EST of the task which has not assigned yet. If it is assigned to the particular task or a particular service, then the execution time on that machine will be used. And we are calculating EST to be the maximum because when all the parent will be finished, we are able to calculate the earliest start time of the child. This is all for equation 1. Let me tell you the equation 2. Moving on to the equation 2. it is to calculate EFT of the task. Is EST plus MET of the fastest machine? Now the third equation. LFT is essentially the deadline. So this D stands for the deadline because this is the latest a task can get started. If we will start the task later than that, we will miss the deadline. So D is the deadline. LFT for TI is equal to LFT of the child minus MET of the child on the fastest machine minus data transfer time. If task is assigned, TT will be 0. So this will be 0 if the task will be assigned. This is taken to be minimum because we are going to start TI as early as we can. We need to calculate what is the latest time to execute TI. We'll consider all child because each child is going to compose a constraint on the parent TI. Child cannot get started until all the parents are finished. This is the diagram we are going to use for all the three algorithms. So this is T entry and this is T exit, and these are the tasks, 9 tasks and 2 nodes. This is the workflow, sample workflow for the algorithms. We are taking this workflow for all the 3 algorithms, and these are the weights of each algorithm, each task. So what algorithm 1 we'll start with? This is determine the available competition services. That means we are going to create a table such as this table of virtual machines. We have 3 services, means 3 virtual machines for the 9 tasks, and we will consider for each task how long it's going to take for each virtual machine to be available. Virtual machine will be allocated dynamically in this paper. Let's move back to the third point. At T entry and T exit, these two will be two nodes with have 0 execution time and 0 dependency. So now we will compute the EST, EFT and LST for each task in G. These, as I showed you the 3 equations, we will use that 3 equations and calculate all the 3 of them. And after this calculation, AST will be 0 and AST T for T exit will be D, because we have calculated all EST, EFT and LST, and we will mark these both as assigned. Now call assignment parent is the second algorithm we are going to use. Let's move on there. Before moving that, I would like to show you this table. The values we need to calculate EST, EFT and LFT. We will take these values as required by the equations to calculate. So in future also, like in algorithm 2, I am going to use this table to see the values and calculate the results. This is the second algorithm. It is going to call all the exit node, and this algorithm is a recursive algorithm. This is a while loop to identify all the unassigned parents. So in the diagram, T exit has 3 unassigned parents, which are T7, T8 and T9. So while loop will have 3 iterations. So let's start with T9. This is the first unassigned parent. In the beginning, partial critical path will be null. Ti is the current task we have to calculate. EFT plus TT, that will be the maximum. Which parent data will be available at the latest? Because in order to execute the current parent task, we need to make sure parent is finished but also data is transferred. So T9 has critical parent T6. Now we'll have to see the critical parent of T6. T6 has two critical parent, T2 and T3, and now we will compare who is the critical parent of T6, T2 or T3. For this we will calculate EFT of T3 and T2. Both EFT of T2 and T3 is 5 and 3 respectively, so we will add 5 and 3 in these ways of the equation. So 5 plus 2 is 7, which is for this one, and 3 plus 2 is 5, which is for this one. So now we going to we will go to the critical parent of T2, which is T entry. So we will not include that as it is already assigned. So partial critical path will be T2, T6 and T9. In the 8th point of the algorithm, it is written call assign PCP, which is algorithm 3. So this means that T2, T6 and T9 will go on one machine. Idea of one machine, will need to make sure we can finish it before LFT of T9. We cannot calculate LFT because LFT means latest finish time, as late as we can, but we are using fastest machine. For this we have to use the slowest machine. EST becomes AST once the task is assigned. And for the 9th point in the algorithm, for all tasks T2, T6 and T9, we will update all the successors for Ti. Successor there means those tasks which are not assigned yet. We do not have any successor in this case. Now we will update the LFT for all the predecessors of Ti. So we will update LFT of T6. So we'll need to modify the latest time of T3 to get better estimate of deadline for T3, and this is calculated backward. LFT of T9 will be is given as 30 because deadline is 30. T9 is running on the virtual machine S2 as I showed you in the table. So from that table we will see the weight of T6, T9 and T2. Now T6 and T9 have same weight, which is 8, and T2 has a weight 12. So LFT for T6 will be 30 minus 8. So 30 minus 8 will be 22, and by calculating the LFT of T6 we will calculate the LFT of T3. That will be 22 minus 8 and also minus 2 because this minus 2 because it is running on some other machine. So this will be equal to 12. This will end with the first assigning of the critical parents. So from now moving on to T8, identify partial critical path of T8, which will be T5 and T4. Now we have to decide among these two which will be the critical path of T8. So here comes by the same calculation as we did for T9, here comes T5 as the critical path of T8. Now we have to calculate the predecessors of T4. It has two predecessors, which is T4 and T1, whose LFT will be adjusted. LFT will be 30 minus 6, that is 24, and also minus 1 because because it's running on some other machine, so it will be 23. And LFT of Ti will be 23 minus S1 minus 4. This will be equal to 90 minus 1, that will be 80. So LFT for T1 will be 18. Now assigned parent will be T8 because T5 have no critical parent. This will move on to 80 entry. T8 has a critical parent T4 and T1 is the critical parent of T4. T4 and T3 are going to run on virtual machine 3. Sorry, T1 and T4 are going to run on virtual machine, virtual machine S3. So T1 is equal to 8 and T4 is equal to 10 units. T1 and T4 are not predecessors but they do not have any predecessors, but though they have one successor, which is T7. So LFT for T7 will be adjusted. EST of T1 is equal to 0. EST of T4 is equal to 8 because T1 takes 8 units. Now T7 is equal to 10 plus 8 plus 1 because T4 is equal to 9 and it's running on some other machine. So this will be the critical parent of T8, which will be T5 and T2. Now we will move on to the third while loop iteration for T7. T7 piece critical path will be T7 as all other paths are assigned. So T4 plus T1 is equal to 10 plus 8 and LST will be 18 because it's running on some other machine. So now our assigned tasks are for virtual machine S2 to S1, it's T2, T6 and T9, and for virtual machine S2 and 2, it is 5 and 8, and for virtual machine 3 and 1, it is assigned task as 3, and for virtual machine S32, it is T1, T4 and T7 assigned task. I have explained you this in that diagram only. This is using the slowest machine and by calculating the cheapest path, but we are using the fastest machine. So the time complexity of IEC PCP-D2 algorithm is ON square. In this performance evaluation, there are some sample workflows which are used, and they are using like two ways to measure the performance of the workflows. One is by using the DAG generator, and one is by using the realistic libraries of the workflow. So in this paper they have done one experiment in which they have taken four points and they have used all these structures. On each structure they have performed that evaluation. So in this experiment what they have taken is 10 different computation services with different processor speeds and different prices, and they have evaluated the impact of short and long term intervals of the algorithm, and after that they have used the normalized cost for the workflow of the execution, and also they have assigned the deadline for each workflow. This is a result for all the workflow structures they have used in their experiment. And as you can see that if we compare all of these diagrams, all of these 5 diagrams, ICPCP is give the best performance than all the other two. So the blue bars are of ICPCP, and the red bars are of ICPCP-D2 and the green bars are of IC loss. In the first one, you might see that IC loss has the best performance, but in all the other, well, in all the other ones, oh sorry, the first one you can see that ICPCP-D2 has the best performance, but in all the other ones you can see that ICPCP has the best performance, and so the overall performance of ICPCP is considered to be the best one. That's all for this paper. Thank you.